In the last video in this series, we looked at the definitions of alkanes, molecules that have just carbon-carbon single bonds, alkenes, molecules that have carbon-carbon double bond or bonds, and alkynes, molecules that have at least one carbon-carbon triple bond. In this video, we're going to continue looking at these three types of hydrocarbons, that is, molecules that have only carbons and hydrogens, by exploring how we can use molecular formulas to classify these types of molecules as alkanes, alkenes, and alkynes, seeing that there will be a pretty straightforward mathematical formula that we can use to bucket compounds based on their molecular formula into what category they would fall under. So with regard to a molecular formula such as C6H12, by the time we finish this video, you will be able to recognize whether that hydrocarbon formula corresponds to that of an alkane, an alkene, or an alkyne without having to use trial and error, guess and check to draw out some potential structures and think about whether you can make all of the atoms fit and fill the octet rule. So as we begin, let's do a little flow chart to remind us about what we are referring to when we talk about alkanes, alkenes, and alkynes. So we previously broke our hydrocarbons, molecules that have only carbon and hydrogen, into three major categories: alkanes, with the A and E suffix, which were compounds that had just carbon-carbon single bonds. We also saw alkenes, with an E suffix, and these were compounds where there was at least one carbon-carbon double bond present. And then alkynes, with a YNE suffix there, that have at least one carbon-carbon triple bond. And there is some additional cool terminology that goes along with this. Alkanes we refer to as being saturated molecules. The terminology that we use here is analogous to the world of saturated and unsaturated fats, where saturated, in both the case of alkanes and fats, refers to molecules where we have maximized the number of bonds between carbon and hydrogen. In other words, the ratio of hydrogen to carbon in these molecules is as high as it can get, because to fill the octet around each carbon, there's no carbon-carbon double bond. Instead, there's only carbon-carbon single bonds and bonds to hydrogen. So saturated means that we have maximized the number of hydrogens bonded to each carbon. So saturated refers to we've maximized the number of hydrogens bonded to each carbon. For this to happen, all of the carbon atoms must have single bonds to one another, as we saw up here in this particular example. In contrast, alkenes and alkynes are referred to as unsaturated molecules, meaning that they have not maxed out the number of hydrogens that they could have relative to the number of carbons in the molecule. Instead, they are molecules without, so WO, the max number of hydrogens bonded to each carbon. And the reason why they don't have that max number of hydrogens is because instead, to fill their octet, they have a double bond or triple bond between the carbon atoms. And so in the case of alkenes, if we were filling in just hydrogen atoms here, we would have a total of 2 hydrogens bonded to each alkene, versus over here in the alkanes, we had 3 hydrogens bonded to each carbon of the alkane, meaning that they are saturated. They maxed out the number of possible hydrogens there. Instead, alkenes have fewer because instead they have a carbon-carbon double bond. And then alkynes are even less saturated because they have, to fill the octet, just 1 hydrogen max possible per each carbon atom. And so this terminology also applies toward fats, in that we describe saturated fats as ones where there are only carbon-carbon single bonds, and unsaturated fats are typically ones where they have at least one or more alkene groups. And that will have some important properties in terms of whether the fat is a solid or liquid at room temperature, and other properties that influence the taste and the way that those fat molecules interact with the body. And we'll get into that in some later segments. For now, as we look at alkanes, alkenes, and alkynes, one thing that you will be tasked with doing is looking at the molecular formula for a molecule and assessing, based on that molecular formula, such as C6H12, whether the molecule is an alkane, an alkene, or an alkyne. And so that is what we are going to focus on here in this video, is how we can apply molecular formula to categorize whether that molecular formula corresponds to an alkane, an alkene, or an alkyne. And this rule only applies for acyclic molecules. That means that the atoms are not in a ring. A ring is, as the term sort of describes there, it's atoms that are connected into a circle pattern, rather than, with the examples we've looked at up here, the carbons are connected into a chain. They don't connect back on themselves to make a circle or a ring. So it's only for acyclic hydrocarbons with one max alkene or alkyne group. So in other words, you could have a whole chain of carbon atoms, and in that chain, all the carbons will be carbon-carbon single bonds, except for one alkene group or one alkyne group, and that's what the formula here that we're looking at will apply toward. And the formula works by relating the number of carbon atoms, so Cn, where N is the number of carbon atoms in that molecule, to H. In the case of alkanes, it's going to be 2N plus 2. So you'll always find with alkanes that are not part of a ring that the number of carbon atoms is related to the number of hydrogens, in that you take the number of carbon atoms, multiply by 2, and add 2 to give the total number of hydrogen atoms that will be present in that molecule. Alkenes are going to be CnH2n rather than 2n plus 2 because they are not saturated molecules, so there's not as many hydrogen atoms relative to how many carbon atoms are, so we don't have that plus 2 in there, we just have 2n. And then alkynes are even less saturated, so they are going to be represented by Cn, where n is the number of carbon atoms, and then we can find the number of hydrogens based on that by doing 2n minus 2. So these are the formulas that we can apply toward this. Let's see how we can use this information toward actually solving some problems. Where would we apply this type of info? So I'm going to shrink this down to give us some elbow room to work through a problem or two as examples of this concept. So we're going to say that a molecule with the molecular formula C6H12, that's the formula that we used on our intro screen, is acyclic. And we're going to say what type of hydrocarbon is it? Meaning, is it an alkane, an alkene, or alkyne? In order to do this, we will match up the molecular formula that we've been given, C6H12, with one of the patterns we see here in our rules that I'm highlighting in yellow here for relating the molecular formula back to whether a molecule is an alkane, an alkene, or an alkyne. Doing this, we see that the template that our example would follow matches CnH2n when we relate the number of carbon atoms to the number of hydrogens. So if there's 6 carbons and H2 equals 2n, it would be 2 times 6, so C6H12, and that matches our pattern that we expect for alkenes. And so therefore we can classify this as an alkene molecule by recognizing that it follows this formula. Here's another regard in which this information about relating the molecular formula to the structure may come in handy. In this problem, we are going to be told that a molecule has the formula C3H8. Provide a structure for that molecule. So in other words, we need to show how the atoms are connected to one another, and we need to show what atoms are connected to who, and show the bonds as lines connecting all of those. So C3H8, by trial and error, we could start stitching together 3 carbon atoms, plugging on hydrogens, trying to determine whether there's double bonds here or here, triple bonds anywhere, or whatever the case might be. And so this formula that we have for determining and relating the molecular formula to whether a hydrocarbon is an alkane, an alkene, or alkyne, we can use here to our advantage to streamline our process here. So there's no longer trial and error, but instead we know that the molecule is an alkane, an alkene, or an alkyne. So C3H8, using our formula there to link that to a structure, C3H8 would fit our template of Cn, where n is equal to 3, because there's 3 carbons. H then would be equal to 2n plus 2, because if n equals 3, that would give us 2 times 3 makes 6, plus 2 is 8, so C3H8. And that formula, looking back at our notes here, equates to an acyclic, no ring, alkane. So knowing that an alkane is a molecule has just carbon-carbon single bonds throughout, that would enable us to fill in the structure of an alkane that has 3 carbon atoms. So I'm just going to put those 3 strung together here with a covalent bond linking each of them, and then filling in 8 hydrogens. And the way that we need to do this is make sure that you're looking at the octet rule. Remember that carbon prefers to have 4 bonds to it, and that's how it fills its octet typically. So we're filling in a total of 4 bonds to each carbon by filling in our hydrogen atoms. And this is creating a saturated molecule. Saturated meaning that we have no double bonds. Instead, we have just carbon-carbon single bonds throughout, and we've maximized the number of those bonds that we have throughout here. And so looking at this C3, boom, H8, and we have the octet filled for all of the atoms. And I'm going to put that down as a note because that is so important that you do have to make sure that you've filled the octet for all of the carbon atoms. Remember that hydrogen has a preferred full valence with 2 electrons, and so that's why we don't fill the octet for the hydrogen, so there's just always 1 bond connecting atoms to hydrogen there. So definitely remember to fill the octet for all of the carbon atoms, whatever you're doing throughout this entire class, whenever you're drawing structures here. But the take-home message is that these formulas are worth becoming proficient with because they will allow us to quickly evaluate whether a molecule is an alkane, an alkene, or an alkyne to classify it, and they'll also give us clues about drawing structures of molecules, which is a key skill that we are going to be applying later on in this unit as well as further down the road.